Welcome to the fractional calculus seminar series. Starting today, we will organize the focus session on numerical analysis methods and singular integral computations. The first speaker for the day is Professor Weihua Deng. Professor Deng is a professor of School of Mathematics and Statistics and State Key Laboratory at National and Natural Product Chemistry, Lanzhou University. His research interests include multiscale modeling, scientific computation, deep learning, and their applications in chemistry and biology. We're very happy to have you, Professor, here. Please, you may begin your talk.
Okay, it's my great honor to attend this wonderful event, and it's my great honor to give a talk in online. Thanks for all the attendees. Today, my talk focus on the, as mentioned, just the professor mentioned, Pavan mentioned, this is on the fractional calculus seminar. So in this model, most of the time we'll use the fractional calculus as a mathematical tools to build the modeling and based on to characterize the natural phenomena. So firstly, we'll discuss about the background motivation. Then we'll build the most models. Then we derive the microscopic equation. Then we do some numerical simulations. Yeah, so the outline is 5 parts. First of all, we introduce anomalous dynamics, even though the attendees, so the audience is experts, but still want to mention the background of our research interests. And then we discuss mathematical modeling. Then we do some analysis and discuss about the algorithm. Otherwise, we further discuss about the applications especially in the chemistry and biology. Then finally we'll discuss the further research topics. Maybe we can share our view for what kind of research we can do further research. Firstly, the motivation comes from mostly from the biology background. So because in the biology system, the system is very complicated. So generally, the diffusion process is not brown. So this is what we are focusing on. For example, for the left one is the facilitated diffusion. There you can see that for the DNA, first is do sliding, then do hopping, and then you can do jumping. So because of this picture will show that generally, if you use a stochastic process to model this the DNA, the process of the motion of the DNA, generally it is no longer Brownian motion. And in the right hand side, of course, is still the protein and the enzyme diffusing in biology cells intermittently bind to the cellular embryo. Again, it's a physical biology background. Mathematically, we can build the models. That means we take the motion of the proteins or enzymes. We take it as consider it as a particle. Then the particle will move first in the plane, then in the first in the 2-dimensional, in the Euclidean space or 2-dimensional in the plane. Then further it moves in the 3-dimension. So I think mathematically it's still is a very interesting. It's very interesting mathematical model because it will be coupled. The mathematical the PDEs should be a 2-dimensional equation coupled with a 3-dimensional equation. Now, further one is super diffusion. As this also in 2006 model it shows the super diffusion for a series of the motion of cells. And in the right hand side, again is this subdiffusion. The left side is subdiffusion, the right hand side is super diffusion. Super diffusion because when we use those again, we use a stochastic process to model to model the motion of the DNA. You can see sometimes the particle. We consider we consider the DNA as a particle. Then the particle can directly access this target. So this implies make a big jump. So it appeared the superdiffusion appears again. Another one for 2D, 2-dimensional fast sliding diffusion. Yeah, for 2 sliding diffusion of TGNPS on the cell membrane, and for the right one is for on the 3D Hoping diffusion. And another more interesting one is about all the previous one is for the pure diffusion process, is for the pure diffusion process. So we consider the particle. So it is conservative. So the particles just do some motion. We can use the stochastic process to model it. But here, this polymer dynamics is still another interesting anomalous diffusion. Another interesting anomalous diffusion. Because in this process, we also consider about the chemical reaction. In fact, because of this is cartoon, this is a picture of the cartoon picture, and for we can consider the polymer is also the micromolecular. For the we consider the micromolecular scale as a particle, but this particle has a lot of monos. It has a long chain, like the right hand side as a long chain. We just consider we focus on the mass, the central mass of the motion. We consider central mass, but while this particle has a lot of long monomers. So when the motion, when the polymer do the motion, the motion do the move, when the particles moves, do the movement, and while the particle do the movement, and also the particles, there are some monomers will be it has the reaction. The reaction implies sometimes it has a polymerization and a decolonization. It means the increase a monomer increase to the chain, or the monomer left the chain. So if this kind of things occurs, it will imply it will make it will make the changes of the diffusion coefficient. The diffusion coefficient will change with the different lengths, different number of monomers. So we will need to do the models. We also need to do some simulation, build the models, build the stochastic process, use an appropriate stochastic process to model these kind of processes. So this all the pictures, all the previous ones show the motivation of the application scenario of anomalous diffusion. Here we again we want to talk about the anomalous is normal. It means anomalous diffusion is everywhere, even in our daily life. Here we give a simple example. Here we give a simple example. As we know, it's a Lanzhou equation. It's also the Newton's second law. As 2 times the derivative of the x is the position of the particles. So this is the mechanical quantity is a force. Left one is force, right one is force. Cosity is noise, is still a force. And mu is a friction coefficient. And x dot is the velocity. And here is v is the potential. So by this one, we can use this model to describe a dot may move in the table, for example. Even for this one, for this our daily life, in our daily life, we mute not this kind of thing not happened in the complicated biology or chemistry the background. But even in our daily life, we still we can use this one to build the model to describe the motion of the dust in the air, and here uses describes the, for example, in the table is the surface of table is not smooth, so we use V to describe it. So for this model, for this one, you can find, someone can find that there are very rich dynamic behaviors, and generally a lot of different anomalous diffusions, not Brownian motion. It depends on the mass of the particles, also the coefficient or mu, and as the following, we summarize the several sentences. And this one not only by numerical simulation, also in some experiments, you can still observe the non-Brownian dynamics. So we call it a Lanzhou picture. So this is also in the way of we build a model by use Newton mechanics to build a new stochastic process to describe some newly observed natural phenomena. And the type of diffusion are usually classified according to the relation of the mean square displacement of a particle to the time t. It can be roughly classified. It can be roughly classified as a localization. It means the MSD of the particle is respect t is a constant. But here generally it's not so intuitive, because the particle is a free particle. If the particle is in some potential, naturally we can observe the MSD is a constant, like a Wally or some, for example, in the harmonic potential with the particles, more generally we can observe this kind of phenomena. But here, not for this motion, for this one, it's not localization. It's not a particle under the potential, under the potential. It's just a free particle. It moves freely. For this one, so it's not so intuitive. It's unintuitive. In fact, we can really observe this kind of phenomena, and also we can build a stochastic process. This process is temporary function Lanzhou motion. Temporary function, you can, if you do the second do is MSD, it behaves like this one. Also, there are some subdiffusion. Alpha is less than 1 and less than 1 and bigger than 0, and normal diffusion, of course, is like is T. But when another is for Brownian motion, another one is important. Not only is second moment, the MSD is a linear function of T, but it's the PDF, probability density function of the Brownian motion is a Gaussian distribution for this one. Not only this hold, not only it holds this holds, it's also the PDF, the probability density function of xt is a Gaussian distribution. But for super diffusion, of course, alpha is less big than 1, and ballistic, and this is t square of t, the MSD. But for polymer diffusion, the MSD still is a linear function of t. It still is a linear function t, but the probability density function of stochastic process is non-Gaussian. Is non-Gaussian. For example, it can be exponential distribution. Also, anyway, it's not Gaussian distribution. So it also we can call it a Brownian non-Gaussian. So this kind of roughly we can call it polymer diffusion. Also another one roughly say it can the strong anomalous diffusion. Strong anomalous diffusion. It means for Q's order moments of the stochastic process, then the Q's order is T related to Q. The order of T is the exponent of T is a function of Q, but it's not a linear function of Q. is nonlinear. Generally, we call this as a strong norms diffusion. So now we can consider what kind of model, what kinds of microscopic stochastic process we can build. So these are all the ways so we build the models. They're also called stochastic models or called the microscopic models. For example, the typical one, we use the serial framework. The most popular framework is one is a continuous time random walk. Another one is a Lanzhou equation. As I just mentioned, the Lanzhou, we build the stochastic ordinary differential equation. We can build and this framework. This is the two popular framework: continuous time random walk and the Lanzhou equation. Of course, there are also other kind of circles, kind of ways to build the stochastic process. But this is continuous time random walk and the Lanzhou equation is the two most popular framework to build the process to try to characterize the natural phenomena. One is Levy walk. We use CTRW can build the process Levy walk. And another one is a continuous time random walk with multiple internal states. Also, we can build the stochastic process as Levy walk with multiple internal states. Well, several minutes later, several pages later, slides later, we'll show this kind of model. And also another one is use this continuous time random walk, the framework, and this continuous time random walk. Another one is the Lanzhou equation in this framework. And this framework we build the stochastic ordinary differential equation to describe the motion of the particles. Although alternating process or resetting process as the other ones, so the other cases, we can also build the in some application scenario we need to build these two kind of process. So for the models, we use the stochastic process or to describe the natural phenomena. And after build we get a new kind of process. The existing process maybe cannot calculate to uncover the mechanism of the motion of the particles. Or naturally, we can in experimental scientists. Most of the times they can always with advance or technology, they always can observe some new kinds of phenomena. And generally use existing process is hard to do some to confirm to be uniform with observed statistics observable. So we as I just mentioned, we need to after carefully considering the phenomena and try to understand the potential mechanisms, then we can build the new process to try to characterize this kind of process, build a new process to characterize the phenomena. After the build the process, we need to study the mathematically or statistically to study the process. One way is to derive to calculate the statistical observables some experimental scientists are interested in, or we can use the statistical observables to study the process or try to uncover the potential mechanisms or extend its applications. So first we can discuss the statistical observables. The statistical observables include a position. For example, the position of particles, the velocity and the position, and also position and functional, and also the functional, and also escape probability. This kind of observable. And also you can calculate the first passage time of the stochastic process. For all this, for this kind of position, for the stochastic position is of course is a random variable, and velocity also random variable, and functional is also random variable. Escape probability. Yeah, it is all these things is a probability density function. We will try to get the probability density function of the statistical observables. But how we get the quantitatively to get the probability density function of the statistical observable, the ways is to try to derive the governing equation. Then first we will try to derive the governing equation. So the governing equation is closely related to the topic of the fractional calculus. So this is fractional calculus seminar. So the governing equation, generally we use to, if the stochastic process is non-Brown, generally you need to, when derive the governing equation will use operators. The operator generally is not a classical derivative. Generally, the fractional calculus will be used. So we try to for one given new processes, generally we will need to calculate the probability density function of the position or velocity position or functional and anyway. So now we will briefly introduce the continuous time random walk modeling. To this model is also a framework to build a new process. The random continuous time random walk is a compound renewal process. For compound renewal, the most popular, for example, the well-known one is the compound Poisson process. Compound Poisson process is implies we can introduce several independent waiting time tau I, tau 1 independent time tau 1 independent tau 2 independent tau 3, and for after tau 1 time tau 1 we make a jump Kc1. After waiting tau 2 the particles will make a jump Kc2. After waiting time of tau 3 the particles will make a jump Kc3. So this build the model is try to try to follow the this is try to make like particles motion or particles use this way, so it will approximate the motion, the trajectories of particles. So this is we build a stochastic process. By this we can define a process, and then by this way, this is we build under the continuous time random walk. We can define new process. After that, we can use that to define live flights. Live flights with for the live flight, the tau I, Kci is it follows the base, the exponential distribution, the waiting time, and this jump length is parallel distribution. So we define a new process. The new process is called the process is called live flight. For live flight, firstly we can calculate the we want to the natural phenomena, the natural observables is the position of the particle, and we want to calculate the position because the position of stochastic is a random variable. We firstly how to calculate the random variable. We derive the probability density function, the governing equation of the probability density function, and the governing equation of the probability density function of the position is this equation. This is the fractional diffusion equation. It's the operator fractional Laplacian. So yes, this well-known operator, not only in the computational community, it's also for the PDE community. It's also most of the mathematicians are studying these operators. So it's in the operator integral form. It's UXT is the probability density function of the position of the Levy flight. And the solution of this one has one single mode, Levy distribution. It's a solution. Is the property of the solution is a Levy distribution. Okay. Also, another statistical observable is functional. A is U is specified function. Is a prescribed function. Is specified a prescribed function. And X tau is a process. Is a trajectory. Is a process. X tau is a process of the. Is a process. So we can also can consider A has a lot of applications in many different disciplines, including biology, chemistry, physics, and also the probability. There are a lot of applications. There are some review papers just discuss the application of this quantity. This is A. Here we try to now what we do. We try to A is again is a probability is a stochastic random variable. So we can if the natural scientists want to get some quantity information or A, we need to derive the probability density function or A, the governing equation or probability density function or A. So it's the governing equation is behaves like this one. Because we do not we ignore to the deriving details here, but in our papers you can get the ways of how to derive this one. For P is the Fourier pair of the A is of A by doing the Fourier transform to the PDF with A we can get the U tutor is a Fourier transform of UAT. So P is the Fourier pair of A. By solving this equation, we can quantitatively get the PDF of A. Again, here appears a fractional Laplacian operator because this is non-Brownian motion. Also, we can. This is the forward Feynman-Kell. Also, if you just interested in the not the joint probability density, you just interested in the functional distribution, you can also derive the backward Feynman-Kell equation. You can also derive the backward Feynman-Kell equation, and also you can calculate the mean. But in order to calculate the mean first passage time, you can get by solving this equation. Again, it's a fraction steady equation, and also you can calculate escape probability. It obeys it follows this is the governing equation of the escape probability. In our paper, in this paper, we derived this equation and do some statistical calculations, and also this process is also not only because this process is jump process, and it can directly from D to E, it can make a jump. But for Brownian motion, it's impossible. This kind of phenomenon is not possible because the particles will continuously do, the motion is continuous. So when the particles move from D left to the D, it must pass the boundary. But for this one, because the process is jump, the particle can directly to goes to from D directly to E. So we can calculate what's the probability for the particle starting from D to go to the domain of E. You can then use how to do it quantitatively. You can solve this equation, and you can directly calculate this kind of quantity. Also, I can give some implications of how to specify the boundaries. How to specify boundaries? Why we physical motivation or how we make the PDEs to be well posed, how to specify the boundary condition from this picture is also give some implications. And another model is the level walk. Level walk is still under the framework continuous time random walk. It implies when we build a new model, we define the tau I distribution of tau I. We define the diffuse distribution of Ci. Then we build a new model. For this new model, for this one, if the tau I obeys exponential the power law distribution, and the jump length, and the jump length is a function is a weight times tau I. For this one, that means jump length is a weight times tau I. By this we define a new process called the level walk. For the level walk, it still has a microscopic equation for the PD. It governs the probabilities, the density functions behaves like this. But here it has this for this one, the equation is no longer for this one, the equation is no longer just a single model. It has at least two modes. For this model, for this one, it has two modes. One is the Levy scaling, we call it central part. Another one is scaling part. Yeah, that means the solution is a little bit complicated than the Levy flight. For the Levy walk one, its solution is a little bit different from, is a little bit complicated than the Levy flight. We say it has two modes. if you do some approximations. First is when x this behaves like with respect to t like this, we call it center part. For this one is x. We can also try to calculate this in this case. For different quantities, for different different quantities, different physical quantities, or for you can get different scalings will play the dominant role for different scaling. And also the scaling limit, we can do the scaling limit of all the CTRW. The scaling limit is corresponding to the time changed level process. We can do the time changed level process, and also can get the for the waiting time, and is power law, and jump length is also power law. We can get the equation with both time functional operators in space and functional operators in time. Yeah, this for the Fock-Planck is this governing equation of the PDF of the position. And also we can derive the for the for the process with power law distribution in both time and space. So yeah, we can calculate the PDF of the functional of the particles. The functional is A, we just defined in the previous slides. And also can derive the backward Feynman-K equation. And also similarly, we can get the you can derive the equation to calculate the escape probabilities. Also, we also build the continuous time runner with multiple instances. This is another application scenario. For this scenario, in this scenario, generally you need to introduce the Markov chain to describe the transition from the one state to another state. And for this one, the system is if the system have n internal states, then the transition matrix n times n. MIG is the state from I to the MIG transition probability. MIG means from the state I to the state G. And when we do summation G from 1 to capital N, then the MIG it should equals 1. So it gets the matrix. So can use get a new kind of process, with multiple internal states. Again, we can derive this kind of process, the governing equations, the microscopic equations. But this equation is a system. It's not a scalar equation. No longer is a system coupled by the equation, coupled by the matrix. And also it depends on the orders of the process, the details of process. In which each state, so it depends on the distribution of waiting times. Also, we can derive the Feynman-K equation. And also the backward Feynman-K equation. Another for this one, we can also calculate the. You can also, if you are interested in the process state in the how long, what's the probability is stayed in a particular state, how long it has stayed. So you can also define this kind of function. Then this function, this kind of AS still is a random variable. Then how to get random variable distribution? Then it's a random variable. So how to quantitatively get to get the probability density function? Oh, you can try to derive the governing equation of the PDF of the AS. So it's an ordinary differential equation, not space operators. So by solving this kind of ordinary differential equation, you can get the distribution over the probability distribution of AS. Also, for this multiple interstates, not only if a process is a physical process have multiple interstates, we need to use this kind of process. Even for a process is not physical, physically you can see it's not a multiple internal states, but for some process it has just one internal states. But we sometimes we try to calculate some quantities. We will try to model this process. Maybe you will meet some challenges, but you can consider it to as a multiple internal states. You can overcome some challenges. For example, for this kind of process, if we try to characterize the process, it from here in this direction, then the process do not return to this three, the three. It just can move to 1, 2, 3. For this process, if it goes from this direction, then the next step is just can go to 1, 1, 2, and 3. It cannot go back to 3. If you try to define this process, it's not so easy. But by other ways, if we consider it as 1, 2, 3, 4 as 4 different internal states, we can easily build a process to describe build a process to describe this kind of processes. Yeah. So it implies that we can for some process when we meet some challenges, we can consider artificially consider it as a matter we can overcome some challenges. For example, for this one, we can use the transition matrix M. It characterizes from here it cannot goes back, and if from here it also cannot goes back, then you use this one 0, 0, 0 means cannot goes back to the coming direction. And other with Lanzhou modeling. Lanzhou modeling is use stochastic ordinary differential stochastic ordinary differential equation to build a new process. Use this way. And for example, by this way, with this for this framework, it also has some advantages. Compared to the continuous time random walk. And this framework to describe the process and some with external potential. If a particle is do some movement in the external potential, generally under the CTRW framework, it's not easy to describe it. But under the framework or Lanzhou framework or Lanzhou picture, it can easy to describe the motion of particle and the external potential. It just at this term. At this term, it describes the process doing the movement, is the moves and the potential. And also we can derive you can derive the probability density function of the position of the particles. And this is the governing equation is this one. If here L is a Levy process, L this is a Levy noise, and again you can if you try to quantitatively to solve this one, you need to get this quantity get the probability density function of the position of the x. You need to solve one needs to solve this equation. You can by solve this equation, you can get the probability density function. Another one we can Lanzhou picture we can use inverse alpha stable Levy process to get some new ways. Also, we can build the new process. Although we can also do some Brownian motion, time change Brownian motion. Essentially, time change Brownian motion is the scaling limit of the continuous time random walk model. Then BS alpha is the time change process. We do some time change to the original one. B is Brownian motion, is the original Brownian motion. When we do the time change to the Brownian motion, we can get a new process. This new process can describe some new phenomena. And here, BS alpha T is alpha stable Levy process, is scaling Levy flight. And BE alpha is a fractional compound process. And also BS alpha 1E alpha 2 is also a new process. But this we get a mathematical way. For this way to get a new process, some probabilists, our mathematicians, sometimes they are more interested in this kind of way to define a new process. Of course, mostly in some cases they are equivalent in some sense to our original one. to the continuous time random walk one. Also, for the particle, for the polymer diffusion, we can build this model. So we can build this model for the polynomial diffusion. For the polynomial diffusion, because it has a reaction, chemical reaction. The chemical reaction means the particles, the number of monomers can increase or decrease. Number of can increase and decrease. NT is the monomers of a polymer. NT is the number of monomers of polymer. When the polymer can, the number can change, but when the number changes, then diffusion, it implies the diffusion changes. The diffusion will change. The diffusion coefficient will change. So the diffusion coefficient is 2D and is a function of the number of monomers. So by this way we build a new process. More quantitatively, the DNT behaves like this one. Is N minima is the smallest number of the monomers. So we get a new process. This describes the polymer diffusion. We call this model a diffusivity model. And for this one, we can derive the Fock-Planck equation and forward from backward and forward Feynman-Cat and backward. This is our newly published paper. As for this one, we derive the models. But this one we use a machine learning method. We use the deep learning method to solve the models, to solve the equations. Yeah, we do not discuss the details, but we just introduce some physical biology background and show the equations. And also the other alternating process is, for example, the alternating process when for the two states for a new process, the process has a level walk changes in the some time interval. It will do the level walk. After that, we will do Brownian motion. Then do level walk. Then do Brownian motion. Then again do level walk. Do level Brownian motion. For this way, we can build this kind of process. And the two process, this is the alternating process. And also this has some richer dynamic behaviors. For this one, it has 3 modes. It has 3 modes. Another one is the resetting process. Resetting process. Here is a resetting process. The position xt or particle is updated by the following stochastic ruler with the probability to goes back to the starting position. Then do the probability with the probability to get this value. We can also derive this forward equation and backward, but here is with a delta function. Here is with a delta function because sometimes with some probability it goes back to the starting position. Anyway, we up to so far we discussed mainly two issues. Well, first issue we use stochastic process to model some new observed phenomena to build the model. The model is the stochastic process, or the model is your mathematical language to describe the motion of the particle trajectories. After that one, we build the microscopic model. The microscopic model is the stochastic process. Then after that, we calculate some statistical observables, the probability density function or the probability observables. How to calculate it? We derive the governing equation of the probability density function of some particular statistical observables like position, velocity, functional, or for all x cap probability. All these kind of a lot of different some typical statistical observables. And this kind of PDEs is closely related to the seminar, the topical seminar. Is use fractional calculus, use fractional space fractional operator, fractional Laplacian. It's also use fractional derivatives in time. After that, we need to study the PDEs. Most of scholars are in the fractional calculus community that do some analysis of the fractional PDEs. Also do some simulations of the fractional PDEs. So after that, we will discuss the PDEs. First one, we can most of mathematical when studying the PDE, you need to do some well-posedness or regularity, do some regularity analysis, or discuss the uniqueness, the existence, uniqueness, and smoothness, and stability, and this kind of issue. Here we discuss use the stochastic analysis to analyze the regularity. But we can use the Feynman formula to do the regularity analysis. We publish in this paper. We do first one for the PD for the Feynman equation. We can formally get the stochastic representation. Then we analyze the regularity of U, and first we show this guy is a unique, mild, and weak solution mathematically. We show then after that we can do some regularity analysis. After that we need to solve the PDEs. When you solve the PDEs, we use traditional method. For example, find the difference. This the early research works for do some. This is still a simple case, but in the practical application, generally the equation is a little bit complicated. For this is the starting, the early paper. They just discusses solving the one-dimensional case, how to describe it. Here we get the finite difference method, use the finite difference with do the discretization of the fractional operators, and also we get some convergence orders. And after that, we use the finite element method. You can use the finite element to do some approximation of the PDEs. We can also use finite element method. In fact, most of the PDEs will not have good research on mathematical research. For example, well-positive regularity. Also, not well studied on its numerical method or numerical. For example, how to design the numerical method for we build the new PDEs, and how to do some numerical analysis to the PDEs, how to get the numerical schemes, how to after getting the scheme, how to do the numerical analysis, stability analysis, and the conversion, and how to do this. Most of the models now very less numerical research and theoretically mathematical research. Here we just the list here in the slide. The list one is just some simple cases. For example, here we just give a simple for this one for the fractional for the steady state equation. For here we just want to show that for some operators, you make some simple change of operator mathematically, you will meet some challenges, and not just follow the original framework to easily do some extension. For example, here with lambda is equal 0. This model is well studied. Some numerical analysis, some numerical scientists already get the framework and do the numerical get some good numerical results. But here when lambda non-equal 0, formally you can see it look like very similar to the when lambda non-equal 0, especially for the variational formulation. For the variational formulation for lambda non-zero or lambda equal 0 is can still get a finite element framework. It works. It's also because all of them are similar. BPB is get the weak formulation of the PDE of the equation for the finite method. The framework is can build, but for lambda non-equal 0, we can for lambda is 0, we can easily prove the well-posedness, existence, and uniqueness. But when lambda non-equal 0, it's not It cannot be directed to do the extension to get the uniqueness, and the existence. For example, when lambda equals 0, by this way, we can build we can show is we can show is use the basic theorem in functional analysis. We can show its continuity and its causality. Then the solution based on the basic theorem or in functional analysis, we can get it has the exact solution. It has a unique, it exists a unique solution. But when lambda non-equals 0, it's this you cannot easily to get this one. Here issue why you cannot, because this guy. Because we can if you try to still follow that techniques to show this equation is well posed, that means it has an existence and a unique solution. You need to try to get this guy. If it holds, then you get succeed, you get success. But unfortunately, this guy does not hold. You can, because of this. So we have to define some new ideas. Here we overcome this challenge. We consider domain this one. For original domain is from A to B, but here the domain is omega star. The original is A to B is omega. Here omega star. It studies from A minus delta to B plus A minus delta to B plus delta. And this extended domain, we define the norm by then use this kind of technique. We get the well posedness of the new operators, a new system. Here we just show a simple example. It implies when the operator makes some small change, some mathematical framework maybe does not work. So I want to see that for all build a lot of different PDEs. There's a lot of challenge. Left a lot of numerical research and mathematical research are left to study. And another one is about the how to describe build the try to solve the Feynman-K equation, because the Feynman-K equation appeared these kind of operators is labeled with also it's called the material derivative or substantial derivative. Again, this is kind of new operators, so we need to carefully to deal with it, carefully to treat it, how to do discretization. After discretizing it, how to do the numerical analysis for the design scheme. So here we just show the ways we use in the frequency domain. We can do the discretization and then get the errors, do some operation, do some analysis, error analysis in frequency domain. After that, we do the inverse Laplace transform. So again, we just give a simple example. And also, we also discuss when the PDEs, also I mentioned the PDE is non-source term. We don't consider the PDE has source term. If the PDE has source term, we can discuss this kind of equation. This kind of equation, if the source term is not a deterministic one, if the source is the source term, if the PDE, if the source term has some random, so we can also solve PDEs with noise. So this is PDE with noise. We also discuss this kind of PDE for the PDE with noise. That means the PDE has a source term. If the source term is a deterministic source, is a random source, then the PDE will have this kind of term. Then mathematically you can also do some numerical study or the mathematical study. You also do some research works for this one. Another popular one is just previously slide I already mentioned is the DBSD. DBSD is worth to do some deep research. Is to do more research for this one. Especially for this one, is unbounded operator, unbounded domain, because tau n is a discrete operator, and starting from 1 to infinity. For the traditional method, it's not easy. We have to do some truncation. Here we can use. We also develop the artificial by using neural network, by using deep learning method. We build the scheme for solving this kind of equation, for solving the operator with infinite dimensional discrete operator. Also, we solve the equation in the continuous operator. Is also in unbounded domain. We can use yeah. Here we just show how to show some details how to develop the BSD framework. First one, the key step is to find an appropriate stochastic process. But this stochastic process is not different. Is different from the physical process. It's just works for the algorithm. We use because the BSD method, the first one, we need to find a process, a physical process, non-physical process. The process works for the PDE. And then we can derive we need to derive the backward stochastic differential equation. But the backward stochastic equation, in some sense, has the same solution as the original PDE. Based on this kind of idea, we can we can design the numeric scheme. This is what we did. Yes, first we derive the BSD, backward stochastic differential equation. Then we build the neural network framework to try to design the scheme. Then we do the discrete. Those are use Monte Carlo method to simulate the trajectories of the stochastic process. But here again, I want to emphasize this process is not the original physical process. It's a process works for the algorithm. Works for the algorithm. So yeah. So we emphasize the first we starting from process. We derive the PDEs. The PDEs is governing equation of the PDF or some special statistical observables. But here when get PDE, we want to solve the PDE. Solve the PDE, we use idea is a BSD method. BSD method we need this method need us to define some new process. So this neural network, the framework, the framework, yeah. Another one is more applications. Is also we have derive a lot of applications in biology. We do some works, yeah. We do some works biologies, and you can do some biology applications, chemistry. Because of time, limited time. Also here we'll just briefly, just 1 minute, we'll close this talk. The house also a lot of much more application motivation. I think application oriented research. This kind of biology, again, macromolecular, we can do the more research works on in this background. I also can do some micromolecular growth in need to do, there are a lot of research topics. And also we can do sediment transport by wind. We can build the use stochastic to model this kind of phenomena and get the anomalous diffusion phenomena. Also can model fluid and solid interaction. Also we can build the enhanced model wind and fluid interaction. Also how can the chemotaxis models for this application, and also have more general mathematical topics. So there are a lot of interesting research topics in the in our research field related to fractional calculus, related to the anomalous diffusion. Okay, thank you very much.
Thank you very much for the talk. For questions, please raise your hands. I don't see any raised hands. If there are any questions, you may please unmute your mic.
Yes,
Yes, please go ahead.
Thank you, Professor, for your interesting talk, and especially for those people interested in mathematical modeling and fractional differential equation. I have just, if you can go, please, page 18, I believe, or 6,
Page
17.
18?
Yeah,
Okay, let me see.
18 or 17.
18. Let me 18. This one? 18, this
Yeah,
17.
17,
This one.
17.
17.
Yes. As I see here in the Fokker-Planck equation, there's
Yeah.
fractional derivative acting on the fractional Laplacian.
Yes.
And the while for forward Feynman cake equation, the fraction Laplacian is acting on the fractional derivative. Can you please explain what's the physical meaning of this?
The physical meaning for this PDE, you mean?
Why in the first one is acting on the fractional Laplacian, while for the one, fractional Laplace is acting on the derivative, fractional derivative.
Why this guy acting this guy?
Yeah.
Yeah, this depends on the deriving details. Because for this one, we use the continuous time random walk in that framework. And the continuous time random walk, we can build the balance equation. Then we use the integral transform. It implies the Laplace transform and the Fourier transform. We get in that frequency space, we can get the equation, the form. When in the frequency space here, this term means t. For example, the Laplace compare or t. For example, we use k, for example, and for the x, for the Laplacian, or for the x in the frequency space, for example, we can use k, for example. So this term is s to 1 minus alpha. Here is k to beta minus 2. So you get the equation. Then you do the inverse Fourier transform and the inverse Laplace transform. So the two terms appear. So that's why it acts like behaves like this. This is because of the deriving process, some details of deriving process. After that, you can also to move this one to the left one using the properties of the operators.
Yeah, my question is, why not the same operator act the same for Fokker-Planck and forward Feynman, both? Because we are, you see.
Why this guy not the same? Your question. Yeah. I see. Yeah. For the Feynman K, this guy is the same, right?
Exactly.
This guy is same, but this guy not the equivalent.
Okay. So is there any physical meaning or mathematical?
Yeah. The physical meaning. Yeah. The physical meaning is different.
Okay.
This one is the joint distribution.
Okay.
This the solution is the joint distribution of the x position and the functional is joint distribution. But this guy is just a distribution or functional. It's just distribution functional. But for the x is just a parameter of the equation. So this guy is just a functional distribution of the. It's just the PDF or functional.
I see.
X as the x0 is the parameter. So the meaning that different meaning.
Okay, thank you.
The backward one, and the forward one. The solution has different physical meaning. The physical meaning are different, and also you change the order operator. The mathematics are not equivalent.
Yes. Yeah. Thank you. Thanks.
Thank you. Yeah.
Do we have other questions? You may please unmute your mic. Yes, I see a question. Please go ahead.
Yes, Professor.
Thank you for a nice talk, Professor Deng. Could you open the slide number 11?
Number 11, okay.
So here you have mentioned that the Lanzhou equation can model the time-changed process.
A time-changed process.
Yeah, so for example, how you rate the possibility of modeling this kind of time-changing process, like a combination of, let's say, the wave and diffusion process. The time is changing, for example, for the first some time, there is a wave process, and then it will be changed to the diffusion. So it is kind of also related with time-changed process. So can we model like with a mixed equation?
Mix the equation.
Yeah, so for some time it's like a hyperbolic, like wave equation, and then becomes like a diffusion. So the process is changing, and it's changing by time. So is it possible to model such processes with such
You mean
a
hyperbolic equation?
like a hyperbolic, then it becomes parabolic after some time. So if we consider all the moment which the changing is occurred, so probably we can model with a mixed type equation.
Yeah, we can do this kind of, you can do by do some time change, you can do this. Yeah. Here applications in this one. Let me see. This one. Yeah, here with this one, by this we will do the time change. This guy we do the time change from the S. We from this original if the equation not this term, this guy describes the variable is S. By use this guy, we do the time change. By do this time change, then the properties of the process, the stochastic process is changed.
Okay.
Yeah.
So I was talking about another case.
Yeah.
Thank you very much for your answer.
Okay, thank you.
Are there more questions? You may please unmute your mic. I don't see any. So I have some questions. So can you go to the last slides of when you have deep you have did this deep learning method that you're using, and you show the loss function.
Loss function.
Yes. Yeah.
The loss function.
I think it's after. Yes, around there. And then next. Where is the
loss function? Let me see. Loss function. Oh, here.
Yes.
Yes, this is the final value.
So, so I just wanted to understand how are you implementing deep learning? Are you using some pins type approach, which is physics informed neural network, to solve your PDE, or how are you solving the PDE?
How to solve the PDE by this loss function? You mean, right?
Yeah.
Yeah. So this kind of method is much different from a lot of method using neural network. For example, there are at least 4 frameworks to use neural network to solve PDEs. First one, for example, for the pins, this is the most popular one, right? It's essentially in the numerical analysis was most of them they think pins, physical informed neural network, as a collocation method in some sense.
Yeah.
Let's just replace the space by polynomial by a neural network. The second idea is by, for example, you can solve PDE based on the variational formulation to transform it as a minimization or functional. This way is still under the classical framework. It replaces the polynomial space by neural network. Another one is adversarial neural network. It's a Petrov-Galerkin, but it still uses the traditional variational formulation of the PDEs. But for this one, for BSD one, it's much different from the I just mentioned the three frameworks. Here, It's much like the machine learning, because here we use the stochastic process to generate the training set. The training set is we generate a lot of samples with the stochastic process. Use the stochastic process to train as the training set. So this is the final value of the PDEs, the final value, and the solutions of the we first we need to do some formally to do that time change. We need to do the inverse formally to let me see to get the so-called backward to t to small t to capital T minus t to do this kind of one. And then try to focus on this one is unknown. We try to solve this one, and then with the loss function we try to make the trajectories value, the final values of the stochastic process is exactly the final value of the PDEs. So the idea is much completely different idea from that existing framework. Here, the key step is we need to build a backward stochastic differential equation. This backward stochastic equation, in some sense, has the same solution as the original PDEs. Why it called it that have the same solution? Because, for example, the PDE, if the solution of the PDE is U, if we replace small capital N by small n, capital X by small x, T as still as T, then the U with small n, small x, T, this guy is exactly the solution of the PDE. But here, we try to get, we replace the small n by capital N, small x by capital X. Then X, we try to, X is stochastic process. We try to find this guy. The equation, that is the equation of this solves the equation. Of course, this equation is not a deterministic equation. Then how to solve it? We generate the samples of X. So we use the samples to train to try to learn the profile of U. This is the idea of the method. So the key step is to derive the backward stochastic differential equation of U. Yeah. Then we need to generate the samples of the X and N. Then try to use this guy as the loss function. This is a basic idea.
I think I understand. Since you already know G, then you can compute this expectation at every iteration, and you can compute G hat, U hat. So G is known.
G is known, exactly.
G
yes.
is known, so you can compute. You can minimize this loss function then.
Yeah, exactly. Yeah.
I see. Yeah. Are there any more questions? Okay, I don't see any. I don't see anybody having any questions. So I believe this is a good stopping point here. Again, thank you very much for the nice talk. It was very nice having you here.
Yeah, thank you very much. Thank you.